All right, let's work through the problem together so we can wrap it up. I'm sure that all of you have already been able to find the mean, right, and the variance at least.
Yeah.
And I would assume we're kind of there. So let's see, before we wrap up this problem, let's see if we can finish it. Let's find the mean and the variance first. I think that one's relatively simple. What I would do just to make my life a little bit easier, I would just tabulate this a little bit differently. So I would maybe put a table with my x values and my marginal probability of x. So here x is 1, 2, 3. And then my marginal probability was 0.2, 0.25, 0.55. You know that the mean is the sum of x times its probability, so I can just multiply these two. And adding these up, I get a mean of 2.35. Did everybody get that for x? Mean of 2.35? The mean is calculated the same way we calculated before, right? Where we have essentially the outcome times the probability of that outcome, and then we add up all of those probabilities of all those outcomes. So remember, mean is one of those parameters that we only calculate for one variable at a time. Okay, so for x and for y. So in this case, my mean is 2.35, assuming that I calculated correctly. I could have already done this thing. No, it looks correct. My variance, on the other hand, is a product of x minus the mean plus u squared multiplied by the probability. So I'm going to get that quickly. So x minus my mean. Oh, I have a Greek keyboard here like I do with my laptop. So x minus the mean squared multiplied by the probability. I think I can figure that out. So we have x minus the mean. Let's fix this cell. Squared, and then multiply it by the marginal probability. If we add these values up, that will give us the variance, which in this case I'm getting 0.6275. So that is my variance, 0.6275. That's the procedure that I like to use, just tabulating it and then just calculating it. And the reason I like to do this is because I can now repeat the procedure for my y values. So in this case, I can write down my y variable and my marginal probability of y. In this case, y goes 4, 3, 2, 1. And my marginal probability, in this case, it's 0.3, 0.17, 0.25, 0.28. I think some of these numbers, all of these numbers, I'm not sure all these numbers are whole numbers or anything, so I'll just reference myself here. Now I just have to repeat the same procedures for my mean and variance, and I'll just replace this to y times the marginal probability of y. Okay. For my mean, I have to add up all these numbers. For my variance, remember, I need to take my value minus the mean of that variable. So I have my mean and my variance for y. I get a mean of 2.49, a variance of 1.409. Let me see if that's correct here. Yep, that is correct. Okay. Are there any questions with the mean and the variance so far, how we calculated them? Is everybody good with how we calculate mean and variance? Yeah. It's the same procedure for x as well as for y. It's the same procedure. Now what becomes a little bit trickier is this covariance and correlation. So before we get to do that, let me just also get my standard deviation. What's the standard deviation for x?
0.7922.
Good. How did you get that?
Square root of the variance.
Correct. All right, good. So we have mean, variance, standard deviation. But now for my covariance, I think the equation said that it was the mean of xy minus the mean of x times the mean of y. I'm going to write down the functions here. You may be wondering, well, what does the mean of xy represent? Well, e is just a function. That's it, it's a function. It's a function, and if I plug in x into that function, I get the mean of x. If I plug in y into that function, I get the mean of y. So all I'm asking for you to do here is to plug in x and y. So wherever you had x, for example, you just have x times y. Wherever you had the probability of x, you have the probability of x and y. So how that would work, it's actually a little bit more tedious the way I saw it, but it's a little bit easier to explain. What I would do is I would take this two-dimensional graph, this matrix, and I would actually tabulate it as a one-dimensional table, which means that I would need to have all my values for x with all my combinations of y. So for 1, for example, I have y equals 4, 3, 2, 1. For 2, I have y equals 4, 3, 2, 1. For 3, I have y equals 4, 3, 2, 1. So we just have to write down each and every one of those combinations. So I have 1, 4, 3, 2, 1. Then I have for 2, the same numbers. I'm going to just copy and paste them. And then for 3, the same numbers. I'm just going to copy and paste them. And of course, all these are 1s. All these are 2s. And all these are 3s. Let me zoom out a little bit so you can actually see the whole table. So it is tedious, I know. But what this table is essentially showing us is every possible outcome in my sample space. 2, 4, it's there. 2, 1, it's also there. So every possible outcome. Now for every combination of x and y, I do have a probability, which is what we call a joint probability, right? So for x equals 1, y equals 4, that probability is 0.15. Just to make my life a little bit simpler, I'm just going to reference this cell. For x equals 1, y equals 3, that probability is 0.02. For x equals 1, y equals 2, that probability is also 0.02. And for x equals 1, y equals 1, that probability is 0.01. Okay? So we're going to repeat the same procedure for all of my cells. And what I have is this nice little, somewhat annoying table. It's annoying because you had a nice little matrix and you turned it into a very long table. But what I can do now is I can follow the same equations for my mean, right? My mean was x times f of x. What this function is telling me is that wherever I had x, I'm now going to plug in x times y. So instead of x times f of x, I'll have x times y times f of x and y. So x times y times the joint probability. And what that looks like would be x times y times my joint probability. And my mean would just be the sum of those values. I'm going to stop here, and you can let me know when I can continue, so you can catch up. But essentially, what we're doing here is we're still calculating a mean, except that this mean considers the combination of the variables by multiplying them. That's all it is. And you can let me know when we can move on.
What equation did you use to get the last column?
Here?
Yeah.
This is x times y times my joint product.
Okay, so just multiplying across.
So just multiplying across all this.
So,
How's it coming, Marco?
good. Done.
Done? Okay. All right.
5.27 is sum of.
Yeah. Good? Okay. So we found the mean of x and y, but that doesn't really tell us anything. What we really want is the covariance. And from the equation, the covariance is this mean of x times y minus the product of the mean of x and the mean of y. So if I write it down, my covariance will be the mean of x times y minus the product of the mean of x times the mean of y. Now what it tells me is that the covariance is negative 0.58. This means there's negative covariance, right? What this implies is that as one of these values increases, the other value decreases. Now the rate at which it increases and decreases, we don't really know it until we know the correlation, which allows us to scale this in a scale of -1 to 1. And from the equation that we discussed in class, the correlation was equal to the covariance divided by the product of the standard deviations. Remember, standard deviations, not variances. This gives us a correlation of -0.6. So notice that it's actually very, very close to -1. It's close to -1, right? So we do have a nice little negative correlation that can be at least quantified using these metrics. So I'll give you some time to wrap it up. Make sure you upload before 5 p.m. at least. And yeah, just wrap up, upload, complete, and this will be your first in-class problem for the semester.
How did you get correlation again?
Well, correlation from the equation is covariance divided by the product of the standard deviations, right? So I have covariance, and I divide it by the product of the standard deviations.
All right.